know, the purpose of the series is to bring community together and to help establish connections between people who might not be able to interact with others in a different setting. So we are very happy to have you here. I would like to thank all the team members of EPSP Connects who help plan and organize these series, reach out to potential speakers, advertise the talks, and make sure that everything on the series information is up to date on the website. Joining me today is Tyler, who will help us with the Q&A session at the end. So Tyler, what is the plan today?
Thanks, Shashank, and hi, folks. I am Tyler Doan. For questions, if you have questions during the talk, please go ahead and put those in the chat, and we will read them out at the end. Alternatively, if you prefer, at the end of the talk, we can unmute you and you can ask directly. And if you happen to be watching or listening to the live stream on YouTube, we will also monitor for questions over there.
So we'll begin with the introduction for our speaker today. So Dr. Zi Wu, he is an associate professor at Tsinghua University in China. He holds the role of associate editor for academic journals such as Water Resources Research and has authored research articles in prestigious journals like Journal of Fluid Mechanics, WRR, JJR Earth Surface, and many more. His research is centered around the particle transport in a fluid flow over a broad range of timescales, and you'll see today some of his research today. So, Dr. Wu, please take it away.
Okay. Thank you, Shashank, for the invitation and also for the introduction. So at the very beginning, I also want to thank every one of you joining this seminar. Some of you may know that we Chinese right now are celebrating the Spring Festival. Although now we come back working, the celebration is not considered done until Saturday. So I just wish every one of you a very happy Dragon Year. So that's Chinese New Year. So come back to my talk today. It's about transport of active and passive particles across scales. So I planned this talk like in 3 parts. First, I will just give a very brief introduction on a concept called dispersion, just in case some of you may not familiar with. And also this concept like formed the basis for a great portion of my research works. And in the second part, we'll just walk you through like very fast, just about my studies about this passive and active particle transport. And in the last part, it's a relatively complete story on Bedler particle motions, which was in collaboration with David Furbish and Effie Fofla. So here we just get started on this well-known concept of diffusion. So I think every one of us here is familiar with this one. If we have a glass of water and just get 1 drop of ink, and inside the water, we will see that the color volume starts to expand, and eventually it will just everywhere inside the water will have the same color, meaning that the concentration is everywhere uniform. So this is like just a macroscopic description for diffusion. So if we look at this problem like from a microscopic perspective, we can see that every one of the molecules of the ink, just they're performing random walk, just due to random collisions with other particles, etc. So these are for diffusion in this glass of water without flow. But what happens if, like in natural environment, we have flow? So here I think is the most idealized case, just like with the linear shear velocity. So what happens if we also have a drop of ink there? So here's what we can observe. Like in the vertical direction, these particles performing random walk, so they can just travel among different streamlines. So in every like a different streamline, they will have different velocity, just to bring this particle downstream at different velocities. So if we look at this process at different time scales for this line source, we can see that every very beginning, it's just expand very much like the shape of the shear velocity. But as the time goes on, we will see that the difference in the vertical direction start to disappear. So eventually, this whole process just looks like a one-dimensional process, just in a streamwise direction. So that's the process first studied by G.I. Taylor in 1953. So for solid transport in a laminar tube flow, they first introduced instantaneous release of solute. And then in a very short time, this cloud was stretched, just like in the shape of, in a parabolic shape, which resembles the flow velocity profile. And then at some larger time scale, we can see that all these asymmetries disappear. Just what you can see is a one-dimensional distribution, like a Gaussian distribution. So it's a diffusion process. So let's come back to like the process in the glass of water. So if we write a one-dimensional diffusion equation, it's like this. And for the teledispersion, we can also write this one-dimensional diffusion equation. These two equations, they're identical, except that they have a different diffusion coefficient. And if we calculate, like for this dispersion process under typical parameters, this effective diffusion coefficient is like 500,000 times greater. So like much faster, like a diffusion in this case. So that's the basic idea of teledispersion, like about the coupling between the diffusion and flow shear. So after the propose of this concept, so it has been extensively applied in different fields, for example, for atmospheric and oceanic transport processes. And here for this figure, we like illustrate the discharge of the nuclear wastewater into the ocean, like that happened recently in Japan, and also what happened in our blood, and also that processes in the microfluidics on the lab on the chip devices. They just normally doing like a mixing processes of different fluids. In our field of hydraulic engineering, we care about the accidental leakage of like contaminants, like we put here in China. Not only contaminants, but also nutrients. If a large amount of them get into the water, it can also be problematic. So formation of dead zone in Gulf of Mexico. Here's just example. That's the background. So later is something about my studies. When I was doing my PhD, I was focusing on the transport of solid contaminants. So it's more like water quality. And then when I got my degree, I started my postdoc in Tsinghua University. And I started to look at the transport of sediments, either suspended or bellows sediments. Or these particles, we can characterize them as the passive particles because they themselves do not have ability to move. In comparison, if we look at like microorganisms, like some kind of algal cells, they will have their own devices to swim. So their like a transport process ought to be very different from the other passive particles. Nevertheless, the transport process of all these particles, I think, can be described by a unified theoretical framework as shown here. For example, for the active particles, was the underlying mechanism for diffusion, for the effective diffusion and effective velocity will be different. So that's where the difference come into play. For the water quality problem, what I want to share with you is a paper that I published almost 10 years ago when I was about to get my degree. So do not worry about the equations there. I just put something there to have the space occupied. And we can look at the sketch at the lower part. And that's almost the same one I displayed at the very beginning of the introduction. So put it here just to mention that traditionally, people think that at this second time scale, when the streamwise Gaussian distribution was formed, they think the vertical or we say cross-sectional concentration distribution is uniform. But we find that that is not the case. Actually, they had like a profound distribution. It had its own pattern. It's not a uniform distribution in a cross-section, but actually, as we've shown here upper here, it's a uniform distribution across a curved surface. But anyway, if you want to weight this process to form a uniform distribution, you need to wait at least an order of magnitude longer time. So that's what we call a third time scale. So here is some studies about the basic understandings regarding this transport process. And the second one was done recently. Okay, not very recently, 22. So it's about the transport process in the presence of reversible boundary reactions. So this has been encountered in a lot of different applications, different fields. For example, hydraulic engineering in rivers, and also like chemical engineering, bulk chromatography, and also in biology, probably the transport of like neural signals. Because coupling of these two processes, the transport in shear flow, and also this substance can get absorbed onto the boundary wall. After some time, it can get released back to the flow. So this process can be very complicated and theoretically challenging. And the first author of the paper is a former postdoc of mine, and he's good at math. So what he did is actually extend this classical method of separation of variables. So now we can theoretically tackle this problem. And what we got is a concise analytical solutions. For example, as shown here, the second order concentration moment. You may argue that it still looks complicated, but when I'm saying it's concise, it's in comparison with the results, published results, like 4 whole pages. And the comparison between analytical and numerical results is excellent, I would say. So now we have this theoretical framework, and we are exploring some interesting problems. For example, now one of my PhD students is looking at this identification of spawning grounds for fish, because for this problem, after the eggs was laid in the fluid, the drifting eggs normally have similar density with water or a little bit heavier. So the transport is more or less similar, like the suspended sediments. One thing is that if we can collect the fish egg at some point, some location, we can put them under the microscope and tell which stage of their process, give an estimation of the time, how long it has been there in a flow. So if we have more information, for example, the mean velocity of the egg population, which is different from the flow mean velocity, we can have an estimate on the place where this egg was laid. And if we have more information about the dispersion coefficient, we can estimate the like a probability density distribution of the plates. So this problem can be like explored under this theoretical framework. And I think this student now is got like some interesting results, and I hope the results will like be published soon, so I can also share with you this story. And another thing is about the transport of suspended, resuspended sediments. Some of you may be familiar with Yellow River, and the lower reaches of Yellow River, the bottom of the river can be several meters higher than the ground as a suspended river. To solve this problem, one of the proposed engineering approaches is to like disturb the flows close to the surface of the bottom. So fine sediments on the non-surface make it resuspended and carried downstream by the flow, and eventually get into the ocean. Here, I think one important problem is that once this sediments get resuspended, this disturbance, how this disturbance can be carried downstream, that is the critical temporal and spatial scale for this process. For this transport to become an equilibrium transport again, basically meaning that how long a distance you need to disturb the surface again to keep this process going on. So this can also be studied under this framework. So, and now we come to the bedrock sediment. At a small time scale, as we displayed here for particle tracking experiments in laboratory flumes. So here, the scales we're focusing on is about centimeters and seconds. And because we can design like a sophisticated experiment, so we'll have a lot of like a detailed data regarding this trajectory. So this will be the story I'm going to tell at the last part of the presentation. And here for large scale processes in the field, and people are also using tracer stones to track their streamwise motions too. But normally this temporal resolution will be much coarser, normally several months or even a year after you release those stones, you are going to trying to recover where they are and to record their streamwise locations. So also provide you with the informations on this transport process. So for this process at relatively larger scale, there's this anomalous diffusion problem, basically saying that the transport of these particles are not a diffusion process, but can be faster or slower than a diffusion process. And given that in engineering, people are using advection diffusion equation to describe the transport of better particles. So this like observation of anomalous behaviors, basically saying that there's some process we're not quite know, which we need to dig into that. So here, what we did is that trying to incorporate some key physical processes like the burial and exhumation processes of the tracers into the active layer formulation. We have done that, and we reach analytical solutions, for example, for the variance of the tracer particles. Basically saying that for this anomalous diffusion, it can be transient. This means that this anomalous process happens during only part of the transport process. For example, at a large time scale, this transport may come back to normal diffusion again, which also means the well-accepted conceptual model may not be correct for the large scale process. And recently, we also like work on some experimental data trying to reveal the effects of the bed forms on the trap efficiency, how these tracer particles got trapped by the bed forms. So some interesting results, including the trapping efficiency. Intuitively, we would expect it to be proportional to the height of the bed form, and inversely proportional to the diameter of the particle. And here we did reveal that experimental results on the trap efficiency, which depend on linearly, on this combination of H over D. Okay, now it's about this active particles. So here is an example, an animation about how this algal cell, how it swims. And the Latin name, I cannot pronounce it here, but just to give you an like an intuitive, like an impression. And actually, like people have like observed the phenomenon like quite a long time ago, that if you put these cells into the tube flows flowing up down, you will see that them just get concentrated in the center line of the tube. But if you get the flow direction reversed, you will see that they started to just get around get close to the tube wall. So that's what they call it, the gyrotactic focusing. It's originated from a difference between the center of the shape and the centroid of this cell. So because they do not overlap, it will the gravitational force will cause a torque, and when it starts to swim, the surrounding shear flow will like produce another torque to make this cell to spin, and stochastically, and also they will have a preferential like a flow, like a swim direction. So in some like under some circumstances, they can be trapped like a certain layer of the flow, just which may explain some the occurrence, the formation of the algal bloom. Okay, so here is a problem related to the biological invasion, a certain mussel called golden mussel. So in the artificial water diversion projects in China, which we use to transfer water from southern China to northern China, this mussel just get into this facility and attached on the like boundary, like the surface walls, like to introduce more like frictions and also like influence this water quality. The mussel itself, at this under these circumstances, they cannot move, but their larvae can swim. So we look into this problem to see how they interact with the surrounding flows and how they interact with the surface, trying to find a spot to settle down, which will have the implication to how to control this kind of invasion. And for the microbial contamination in municipal water supply network, the problem kind of similar. And other application, I'm not going to get into details. What we did here is to look at how what is the transport process for these cells in the open channel flow. So we started from the Gamma equation and extended the GEOS method. This method was used previously just for the passive particles. Do not worry about these equations. What I want to say is that now for this key parameters K1, K2, we can capture also these transient processes before it's reached constant. And we can show this two-dimensional distributions to demonstrate how the theoretical results works pretty good. And people also interested in how turbulence affect this process. So basically, it make the distribution of the organisms more uniform vertically, and eventually will affect its streamwise distribution. And here, if we look at this vertical distribution, we can see that if it is the swimming dominated process, basically most of them will just will be concentrated close to the surface. But when the turbulence is playing the role as dominating factor, it will just disperse the concentration to get a uniform distribution. So that's how turbulence will contribute to the distribution. There's still more to come, but I'm not going to present here. So at the last part, it's about a story about the bedload particle motions. Bedload particles can be seen as part of the bed surface when they are not moved. But once they get entrained to move, they can be rolling, sliding, or flotating, at the region close to the surface of the bed. So when Einstein first studied this problem, he just divided this whole complicated transport processes into two elements. They just resting when this particle did not move at all, and we call it hop when this particle was entrained and successively moving downstream until it stopped. This whole process, we can call it a hop. So recall the figures I displayed previously. When we look at this small scale process, we're actually trying to get more information regarding this hop processes, because those trajectories, we measure them from the start of its motion until the end of its motion. There are different trajectories. We're trying to get more information on the hop. So the database we were using was provided by a research group from Vanderbilt University, led by Professor David Furbish. So the high-speed camera was recording this trajectory at 250 frames per second, and the mean diameter of the uniform sand is about 0.5 millimeter. So here, for those trajectories, we have them colored in red and blue. The red ones are relatively short, and the blue ones are relatively long. So how to distinguish between the short ones and the longer ones? So we leave it to the story later. And this study, I think, all started from a figure in this JGR paper. So when they have this experimental data, so in this paper, they put the data points into this log-log plot. Horizontal axis is the travel time, so that's the time for the hop. And the vertical axis is the hop distance, so it's the distance for the hop. So every 1 point in the figure means a single hop with different time and the distance. So there are around 4,000 of them in this figure. So when they put them here, we can observe a relation, a quadratic relation. But not everywhere this trend is so obvious, because if we look at this part, it does not look like a quadratic relation. And the author is trying to explain it as a censorship effect, because the observation window during the recording is limited. So the streamwise scale is less than 8 centimeters, basically meaning that any hop longer than this 8 centimeters will not be recorded. It's like all the data points are chopped off. So I was not quite convinced by this explanation. So that's the motivation for the study. The theoretical starting point is this Fokker-Planck equation, also proposed by Furbish in a 2012 paper. It's an idea borrowed from statistical mechanics. It's about the PDF of the particle's velocity, but it's challenging if we try to use them because we do not know the exact form of the functions mu and k. We know it's dependent on velocity u, but we do not know what mathematical form they are. So what we did is that we look at the definition of mu, for example, and then also look at the empirical data. So basically, mu, the definition says it's the average velocity acceleration conditioning on the velocity u. So we calculate all those green points, which says that mu everywhere is 0. So this is an empirical conclusion. We do not have theoretical ground for that. But anyway, with this, we can determine k in the form of exponential function. Now we can do numerical simulations, particle tracking, Monte Carlo simulation. And we have these numerical results for velocity, acceleration, travel time, and hop distance. The PDFs agree with the experimental measurements very well. So this gives us the confidence that we are actually simulating the same process as we observe in experiments. And then we can put the numerical results into this same log-log plot. We can see that the overall shape of the numerical data, numerical points are very similar as this experimental data. But for the numerical simulation, we do not have censorship effect. We can always follow the particles from start to the end. But still, here we observe certain kind of transition from the red line to this blue line. If we do an average, like averaging across like different hop distances with the same travel time, the transition is more obvious, like from one slope to another one. So this result basically tells us that we can at least divide all those 4,000 point trajectories into two groups. One group with relatively short hop distances, and another group with relatively longer hop distances. And the scale, temporal and spatial scale, is determined by this transition. So that's how we determine in that figure at the very beginning why some should be red and some should be blue. And here's some example regarding this long and short hops about how its velocity variation. We can see that for the long hop particle, the blue ones, the mean velocity is higher. If we look at this scaling, we can actually calculate the mean velocity, saying that for the blue particles, that's long hop particles, the mean velocity is a constant. But for the red ones, the mean velocity is not constant, kind of dependent on how long a time it can travel. On the average, the longer time it can travel, the mean velocities are like higher. This is very important because we're trying to use it to explain why in literature people have different results on the velocity distribution. For example, for a Gaussian distribution here. So we actually look at the Ansi and Heyman, their work. They're using a mean reverting process trying to describe the variation of velocity. And they solve, based on this equation, the truncated Gaussian solution, which they fit to their experiments, and it works well. And they were saying, okay, the results are like indicates truncated Gaussian instead of the red line as the exponential. But at the same time, the authors also point out that the mean revert process can have a crude approximation for the velocity, like this one. So basically, it says that the velocity of the particle can be approximated by a mean velocity plus kind of like a white noise, random fluctuation. This description immediately let us recall our previous figure, because we were saying only those blue trajectories, they have a well-defined mean, because the mean velocity here is a constant. The red ones, they do not have a constant velocity. So here we observe two kinds of trajectories. Only the blue ones, like the same as the what analyzed by Anson Heyman. So this gives us the theoretical expectation that if we look at only those long travel particles, we should have the results as a truncated Gaussian. So we did that, and the results does show that if we consider only these long hops, the results should be a truncated Gaussian. But if we take into account all those particles, the results is this exponential, as indicated by the dashed blue lines. And this shows the tail of the two distributions, and this truncated Gaussian and the exponential indeed look different. And for the hop distance distribution, it is neither the exponential distribution as proposed by Einstein, the blue ones, nor the Weibull distribution as proposed by Furbish. It's a combination of the two. So for the head, it's the Weibull, and then it transitions into this exponential tail. So this is also due to the two groups of the particles, the short hops and long hops. So the story itself is simple. We identify two regime scaling, the transition of the scaling. So we know that there are two groups of particles. So these different characteristics of these particles contributed to why there should be different velocity observed in literature, and what should be the hop distance PDF. But here we know there's a transition, but we do not know. We do not have a theory to explain. Since we were performing numerical simulations during this simulation, so we were expecting, we're trying to see if we can have some theoretical results. So what we did is first we look at this variation of the velocity of a particle during a hop. So at the beginning and by the end, the velocity is 0, but in between, kind of velocity fluctuation randomly. They fluctuate randomly. So the first thought is that we trying to use this random walk to describe the variation of particle velocity. So this is the discrete form of the stochastic differential equation. And what's important here is this random number R. It has a 0 mean and a unit standard deviation. And we also want it to be a Gaussian random walk. Because if this is the case, we will have a governing equation for this process, because it's random walk can be described by the diffusion equation. So, and then how do we know if it is the case? So if we look at the left equation here, what's under this square root sign, this is a constant. So the distribution of R should be the same as the distribution of delta U. We can check the data to see if it is the case. But the results shows that the distribution of delta U is Laplace instead of Gaussian. So what we expected at the beginning is not the case. So what we do then is, okay, if we based on the velocity axis, it is not the case. Maybe we can do something to the velocity axis itself. We manipulate this axis. Someplace we stretch it, someplace we compress it. So here we can see this velocity mapping. Here is a sketch. On the left is the velocity u. So if we walk from the origin, the velocity increase as the distance. But on the right-hand side, if we walk through the origin, the increase of velocity just is like a nonlinear increase and not like a increase proportionally. So that's like a just illustration. But what I'm not going into the details, but here what I want to say is that we can theoretically determine this kind of manipulation we need. And then we can say that in this new axis, zeta, the particle, how they change their velocity in terms of zeta is like in a random walk manner. We check the data zeta and see that, okay, they're like pretty close to this Gaussian distribution. So we can use this as an assumption to obtain the analytical solution. And it turns out the analytical solution works pretty well here, and there's no adjustable parameters. And last, we come back to the Fokker-Planck equation at the very beginning. People may ask why you have a Fokker-Planck equation. Why don't you just start from there? Okay, two challenges. First, we do not know the boundary condition, how to specify this one at the beginning. Just to say that under what circumstances the particle will stop. And the second is that in a diffusion term, this diffusion coefficient is not a constant. It's dependent on velocity. So we do not know how to deal with that. So in a recent work, what we did first for a boundary condition, we proposed just a third type boundary condition, for the stop of the motion. And then we devised the transform, which will just map this Bedlow transport process into a solid transport process. So due to this transformation. So previously, the process we do not quite familiar with, that's the Bedlow transport, now becomes something that I'm like kind of familiar with, because we studied a lot of this solid transport problem under this boundary a reaction. So we can use the theoretical framework we proposed at the beginning. We were mentioning that one. And to deduce this analytical solution. And it's also great that if we replace this boundary condition with another one, I'm not, I don't show it here, but by doing that, we can consider the alternating between hops and resting, just to study this whole transport processes under this framework too. So that's what we are doing at hand, and hopefully we'll finish this soon. So with that, I conclude my presentation, and thank you for your attention, and I'm happy to take any comments and questions. Thank you.
Thank you very much, Dr. Wu. That was excellent. Does anybody have any questions? If you do, please post them in the chat or raise your hand, and I believe we can unmute you if you would like to ask a question.
Roberto, I think, raised his hand.
Yeah, that was a clapping hands, but I do have a question. I was just giving the audience an opportunity. Okay. Anyway, great talk, Z. Thank you. I'm curious about your thoughts on, this difference between short and long hop. Is it either or both flow properties near the bed, or differences in particle size density?
I think the dominant factor will be the flow condition. So like supercritical or subcritical. So because people, when they're doing their experiments, this condition, for example, for the ANSI, their experiments is different from what down there by David Furbish. And also, I think particle diameter is its effect can be in combination with the flow strength, I think.
Okay, thanks.
Do you have any more questions coming?
If people are still typing, I have one question about the very first example that you showed about Taylor dispersion, because I always thought there were two time scales, and I got to see a third time scale in the
Here.
dispersion. Yes. Can you just like very physically what is happening there? How there is an introduction of third time scale?
Okay. So I think it just at the very beginning, people, I think they just kind of confusion here. Because recently we have some techniques like the two-scale perturbation analysis. At the lower, the dominant order, like zeroth order, you will see that this order, it do not dependent on the like a transverse coordinate, which basically means it's transversely uniform distribution, right? Because it just simplifies into a streamwise variable and time variable. And that zeroth order also obeys a diffusion equation. So this is like what people are trying to understand, that when the streamwise like Gaussian distribution was formed, the transverse uniformity will also form. That's something like automatically get into the mind of people. So, but as we show here, it's not the case. When the like a longitudinal normality has formed, meaning that the Gaussian distribution for the mean concentration, it holds. But if we look at this time scale, just T star equals to 1, the transverse, like the spatial patterns, is something like this one. It's a uniform distribution across a curved surface. And when it reduces to the uniform distribution, we can kind of envision that these curves separate from each other longer and longer distance, so that if you draw a cross-sectional plane there, the concentration difference in this plane will just decrease, something like that. So it's the uniform is still an approximation.
Got it. Thank you.
I got another. If that's okay, you showed as part of your motivation, tracer studies, how things, contaminants spread out in different environments within our body, in river systems, etc. What steps are missing, if any, to blow this up to the longer, time scales? You showed, the Phillips tracer experiments with the year and kilometer time scales. And then most of the at least that was my understanding of your model, and what you're trying to fit is those experiments from the lab. How do you connect those two?
Okay. So first, it's about the idea. I was trying to display here. So at the very beginning, if we look at, actually, this is experimental measurements about the bed surface. So it's elevation series. It's get up and down, so meaning scour and the deposition events happening. So if we just take this surface as a reference, basically meaning that those particles buried there were doing relative up and down motions. So that's how we work on this model. These particles are doing random walk vertically in substrate, but only when they get onto the surface, they will have the chance to travel downstream. So that's the basic idea of this model. Then when in terms of calibrating or this model, we will use this surface fluctuation measurements, how often they can just get scoured and get deposited on this frequency. But what I want to say here is that based on this vertical exchange, how frequency it can change, it will determine the time scale until when it will eventually approach normal diffusion. And here for Philip, their experiments, because this in the fields, those particles, the stones are not always in motion, because most likely they will move in the flat season. So during a year, there is a very limited time period they can have the chance to move. So that basically means if you only take out those time has the potential to move these particles during a year is just a very short period of time. So this is why this is why this process is so slow. Like during a year or several years, just do not move that much downstream. And another thing is that this during the flat season, this I think in the field in a like a riverbed, they are scoured or deposited in the same manner as we formulate as I demonstrated just now. This kind of a fill and scour process will cause this burial and excremation of all these particles. So I think I haven't been using directly this tracer field tracer data to calibrate the model, but alternatively, I've been using how the variation of the virtual velocity, because at the very beginning it doesn't move, but 1 year later, the centroid of those population move downstream a little bit. So basically, if we think they are continuously moving, so that is during this period, that is the virtual velocity. So during this transport process, this virtual velocity is like a kind of decreasing all the time. We can have analytical solutions for the virtual velocity. It's decreased in the same manner that's power law decrease. By comparing these two, we will have estimate on the time scale, by which it can reach this normal diffusion process. In the paper, we have that figure, and the estimation in my mind is about like 20 years.
Yeah, my thoughts were going towards and I think you alluded to this in terms of the frequency at which the particles are exposed. So the flood season could like an intermittency factor or
Yes.
a flow duration curve. You know, you can only move if you're above this, and that only happens so much time of the year. So that's how you would connect your, particle scale to the reach kind of scale.
Yeah.
Thank you.
If it's okay, I can ask another question, which is,
Sure.
I think, somewhat related to this point. in the very last scaling two regimes, is there a very peculiar point where the two regimes intersect? Like at some point you transition from one regime to another, right? Like long versus short. So I could see like an intersection point around 0.1.
Yeah,
Is
so that's the scale, 0.1 second. So when we say scale, it is not exact time, but around that point of time by an order of magnitude. So it's around 0.1, can be 0.2, like between 0.1, 0.2, or even.
And how
like,
does that change? Like what is controlling that scale?
I would say because actually, if we look at this velocity variation at the the rate scaling, that's the quadratic scaling. During this scaling, I think these particles are using most of their time accelerating or decelerating. So like an inertial effect plays a very important role. But if we look at the particles travel can travel a long time, so like shown here by the fluctuations, they can have velocity fluctuations, but when we do an average, it's just fluctuating around a mean velocity. But the inertial effect, which means it is where it gets started to accelerate towards this mean velocity and eventually stop decelerating that phase, the proportion of these two phases just occupied a small portion for the length hop trajectories, I think. So that's contributed to the difference between the two.
Got it. Thanks.
Okay. We are approaching the hour, I think. So I think we'll go ahead and thank Dr. Wu again. That was a really fantastic talk and a lot of really great work. So thank you for sharing that with us and congratulations on good work.
Thank you. And I would especially because when I see your name here, it also reminds me of those days visiting David Furbish and this problem. And I think a lot of material here for this story came from the collaborations with him. So
yes.
For me, it's good to see you here.
Yes, I'm very pleased to hear that. Well, thank you again. And yeah, great work.
Thank you everyone for joining. We have another talk in next month. So we'll send a reminder soon to everyone. But it will be on March 28th by Dr. Anastasia Pilores. So thank you once again for joining, and we'll see you soon in the next talk.
Thank you.
Z, that was really fantastic.